Let's take a look at mean and expected value for discrete probability distributions. And the best way to describe this is by example first. So let's take a look at this idea where, so x is a random variable and p of x is the probability of x. So, and it could be not just like selecting random events, but like the example we're going to look at is number of times a sample population in a community goes to the store and what are the chances, how many times a week. That was the question. We'll do that one. So let x represent the number of or frequency of something that occurs. So for example, number of heads, they do that example in the book, one of the books. Number of times or trips to a store, we'll do that one. Number of shots, could be free throw shots or basketball shots, could be shots that the whatever, made up something. Number of whatever. So this one is a probability distribution, and there are so probability of none, 1, 2, or 3. So this is the number of, and when I use that symbol, I don't mean pound or hashtag, I mean number. So if this is 1/8 and this is 1/8, this one actually ends up being symmetric. Let me erase. So if I erase this one and I say that one's 3/8, then what does the middle one have to be? Well, and remember that the sum of the probabilities of p of x for discrete must equal 1. So 3, 4, 5. So the middle must as well be 3/8. 5, 6, 7, 8, right? So it must be 8. So it has to be that. So you will always know that. And that concept that I just did is a degrees of freedom thing. So there are 1, 2, 3, 4 data points, but there's really only 3 degrees of freedom because you always know the other one. Just roughly, a rough idea. All right, so the expected value is basically the idea of would you expect to have 0, 1, 2, or 3? And this one is symmetric. So this one, what should it be if you have a symmetric distribution like that? You would expect what? Ponder that as I erase this. I made a real rough frequency distribution histogram. Well, I can do this, can't I? Looks like that. Relative frequency histogram, sorry. Of that one above. And you can see that you have 0. I mean, again, let me erase that. So those are good when I want them, not good when I don't. So you can see that, whoops, let's go back, that you have 0, 1, 2, or 3. Again, I made this really rough just to show you, you can sketch them pretty quickly. This is at 1/8, this is at 3/8. And so this relative difference is what you are wanting to see. So you're not changing the scale here. If you did, then that is skewing data. That's what people do all the time. They make it look nicer and huge different values when things like that. And this distribution ends up being like the bell curve thing. This is only 3 data points. When you do the bell curve thing, the normal distribution, it's infinite, assumed to be. So the balance point or expected value you could see just by looking has to be in the middle, has to be right there. And that's kind of like if you do a histogram, that's what's teetering, and that's where the balance point would be. So how you calculate that is the expected value of x. So here's the definition. So we let x be a discrete random variable probability distribution P of x with a probability distribution, I'll abbreviate both of those, P of x. The mean or expected value is given by this. So we say mu, so population mean, or we say expected value of x is equal to the sum of x P of x. So you multiply x times P of x and add them all up. And I didn't put any indexes in, but we say this is overall x values. So I didn't put in x bys and all that stuff. So if we calculated the one above, let's just do that one. So we have mu is equal to the sum of x P of x. So we could put I in there this time, and I goes from 0 to 3. So now it represents those values. So that would be, that first one, 0, is always going to zero out, but I'll always like to put it just to remind myself what it looks like. 0 times 1/8, 1 times 3/8, and that's a that's a times, not a 1 3/8, and then another 1 times 3/8, and then a 1 times, oops, not 1, 0 1 2, and then 3 times 1/8. Let's make sure these lined up right. So 1/8, 3/8, 3/8, 1/8. Okay, and then 0 1 2 3. 0 1 2 3. Here's your x. There's your probabilities. Okay, got it. So you do that calculation. Go ahead and try it on your own, and you will see you get 1.5. Excuse me. I'll do it on my calculator as well. So the first one's 0, and then 3/8, so 3 divided by 8. Actually, I'll have to do it on a different one. I recommend like a scientific one for this type of stuff, not just a 4-function one. Those don't do order of operations at all. It messes it up. So I'm just going to do it on my small iPad. Okay. So 3/8 divide 2, excuse me, and then 3/8 multiply, and 3/8 again, and I got it. Okay, so I got 1.5. Oh, it's backwards. I always forget it's backwards when I do that. I'm sorry. Okay, so that's what you get there. All right, let's continue. Let's look at the standard deviation or variance. Okay, so you could talk about this being x bar as well for expected value for this case. So sigma is equal to the square root of you take each x, subtract mu, or x bar, and square it, and then you multiply by p of x. Okay, so that's standard deviation of random variable. Standard deviation of the random variable x. So, oops, I totally forgot to write in there. I don't know what I'm doing here. I must have been coughing or something. That is the sum. You're summing all those up. And then you're doing the positive square root. So these are all your random variables, x1, x2, x3, x4, x5. Probability of 1, probability of 2, probability of 3. Actually, you start at 0, right? So 0, 1, 2, etc. And then here's your probabilities of each one. So these have indexes. It's just easier to think about it when they're off. When we do the example, we will go over that. Okay, let's go ahead and do this example, 4.85. I'll read it first, just like I always usually do in class. Let x represent the number of times a customer visits a grocery store in 1 week period, in a 1 week period. Assume the probability distribution of x is given by this. So this is the number of times. So either they don't visit, visited once, visited twice, visited 3 times. You can see that this is equally distributed. It's not skewed in any way. Find the expected value of x. So we already know the answer to this. Because this distribution is symmetric, then it has to be 1.5. We know mu must be 1.5. That is the expected value of x. All right, so let's see if that's what we get. So it's like you're verifying it. All right, so you know that mu equal to, so this is like making the assumption that you know the entire population. So we're using mu in this case, which is the expected value of x. And it is the sum over x sub I, p sub I of x, and I goes from 1 to, so you can call it 0 or just 1. It doesn't really matter. So you could say that this is like I goes 1, 2, 3, 4. It's just an index, so it doesn't matter how we state that really. So we'll just do 1 to 4. So there's 4 terms. So it's equal to 0 times 0.1 plus 1 times 0.4 plus, and I always do this, I'm going to move this down. There's my mu. Plus 0, 1, 2 times 0.4 plus 3 times 0.1. Okay, so we calculate that, and you will see you get 1.5. So 0, 1, 2, 3, so it's got to be in the middle because it's a symmetric distribution. Okay, so that's what you get. You can check it if you'd like. All right, so now let's go ahead and calculate the variance, and then we'll do the square root to find the standard deviation. Okay, so it didn't ask that, but I figured we should practice it. So I'll show you how you do that. So it's the sum over all the x values. You're going to subtract mu, and then you're going to square it. and you're going to multiply by p of x. So what you get is 0 minus 1.5 squared, and then the corresponding p of x was 0.1, and then plus 1 minus 1.5 squared times 0.4. And I'm going to go ahead and wrap this back down so it's all in one line. So we'll wrap it over to here. So we can see it going all the way across. Then plus 2 minus 1.5 squared, corresponding p of x for 2 is 0.4, plus, and then it's 3 minus 1.5 squared times your 0.1. And then you want to calculate that. What I'm going to do is go ahead and use the calculator and do it like really by hand and see what we get. So I'll tell you what I'm typing in. Yeah, probably easiest. So just type it in like this. It'd work okay, I think. So 1.5, you're squaring that. And then you're multiplying by 0.1. And then you're going to subtract 1.5 and 1. And then you're squaring that. You're going to multiply by 0.4. We get 0.1. So I get 0.225, 0.1. And then I'm going to add all those up. I guess I should write it down because the way this works, it all stays on a stack and you just can add them up later. 0.1. Okay, and then 2 minus 1.5, and then you square it, and you multiply by 0.4, 0.1. And then 3 minus 1.5, and we square it, and multiply by 0.1. And it's the 0.25, which we should expect that to be the same, right? It's 0.25 again, 0.225. Add all those up, and you get 0.65, and that's the variance. So you take the square root of that. Let's try that again. So sigma is the square root of 0.65. And you get 0.806. All right, so that's the standard deviation. And what that's of x, so it's how spread out x is. And so if you look at the back here, one standard deviation, basically you're saying you're here, so you're getting both of those values. You're going on the outside. 2 standard deviations is 1.6. So if you do 1.6 plus 1.5, it's 1.5, you get what? You get 3. Well, that's, of course, outside. That includes everything. So not a lot of data points to work with, but that's what we're getting. Okay, so that's introduction to discrete random variables. Now we go on to the next part of that.